So if things feel a little, what's the word? A little discombobulated, they are. Um, I rearranged my basement so that I could get stuff ready to go back to the classroom. And since they denied all my requests for um, setups and things in the classroom, I'm gonna have to break down the display, the thing I have going, so and to bring stuff back. And they said, you may not have an extra monitor. I'm like, why won't you give me one? They're like, well, kids are coming back. I'm like, bro, you don't understand the situation, but whatever. Oh, I was recording through all that. Whatever. Anyways, it's frustrating, but here we are. I'll keep working through it somehow. In the meantime, let's spend some more time on substitution. So these are the 6 that I asked you to look at and think about since the last time we met. And hopefully you spent some time doing that. I have 1 or 2 things I want to talk about first, but then we can go back if there's 1 or 2 of these you'd like to work through other than E. E's a special case. Like if you don't see how E works, that's fine. E's really nice for finding out the substitute, for identifying G of X, G prime of X, F prime of X, what all that stuff would be. It's pretty nice for all that, but just remembering what the antiderivative of an exponential is. Otherwise, these aren't terrible, but I'll gladly work through whichever ones you'd like after I do the other thing I need to do. I also have solutions from students from previous years, and this middle one was me. So you can also come back to this presentation and check out what I've got for these answers. But here's the big thing that I wanted to do today is I wanted to evaluate a definite integral. Oh, shoot. I forgot the most important thing. I forgot to say hellos. All right, we're going to pause recording, resume recording. All right, here we are. So again, our goal here today, folks, we're just going to try to evaluate this definite integral by hand. Now, at the very end, after we evaluate it by hand, we'll go back through and check it with a graphing calculator just to make sure. Okay. So looking at this, I know I need to use substitution to help me out on this because I don't see a particular pattern, many of our common patterns that we usually use. And again, to look for common patterns, you want to look at lesson 4.4. In there, there's a table of common, what's the word? Like the common basic integration rules. So I'll go take a look in there. If it doesn't look like any of those, you probably need to use substitution or rewrite it somehow. I'm looking at this one and I just don't see how to rewrite this. All right, it doesn't look, let me rephrase. I can see how to rewrite it, but that's because I know what I'm going. When I look at this, it doesn't look like any of the common patterns I have. I see a square root, but there's also something else going on. So I'm going to try a substitution and try to help me out. Try to determine what's my inner function going to be. And again, the inner function, what U is going to be. That's kind of a more formal way to think about it. What's the inside function? Well, looking at it, I think I have 2 choices, truthfully. I think there's 2 choices. I can either let it be x plus 1 or 2 minus x. And looking at those options, I think the one side of the square root, 2 minus x, is probably the way to go. I could potentially pick the square root of 2 minus x, but that seems kind of complicated. And usually I don't want to grab that much. It feels like I'm taking too much of the equation of the integrand. So let's see what happens if I let u equal 2 minus x. So if u equals 2 minus x, then du, taking the derivative and multiplying by dx, I get du equals negative 1 dx. Based on what we did the other day, I'm going to just solve that for dx so I can just plug it in and see what happens. All right, so now that I have u and solve for dx, I'm going to substitute these 2 things in to the integrand. Boom, I've substituted them in. Okay, well, it kind of made part of the integrand simpler, but I still have this part to deal with right here. And that's a little bit of a conundrum. Like what to do with that? By the way, this is another thing to note. These were X values up here, the lower and upper bounds. They are still X values. I'm just typing that in there to remind you that these are currently X values. You know, it'd be nice if there was some way, coming back to it, some way to get rid of this X plus 1, some way to write that in terms of U, so I only have U's here so I could like play around and do something productive with it. I do have this equation over here. Let U equal 2 minus X. I feel like I could solve that for X. And I can. If you do, let's see, if I add X, subtract U, I get 2 minus U equals X, which is kind of a handy dandy nifty feature here. All right. What I can do now is take this U expression, 2 minus U, and plug it in for X right here. Not up here yet, but right down here. And simplifying that, I get 3 minus U. Because 2 minus U plus 1 simplifies this piece, turns into this. Now, that's particularly advantageous for us because now I can kind of multiply things out and get things to look more like I'd like them to. Now, there's one more issue that we need to deal with before we move forward and actually go and like do the anti-differentiation and go from there. These values are X's. Those are incompatible with U. I need to rewrite them in terms of U somehow. Gasp. Alarm. Noticing. U equals 2 minus X. I could just feed each of these X values in their current position into this U equation up here. So let's do that. If I feed 2 into that, I get U equals 2 minus 2 equals 0. If I feed negative 1 into that, I get 2 minus negative 1 equals positive 3. Now, I could have put U equals 0 and U equals 3 with these, but because there's no other variables other than U now, it's implied that these are in terms of U. All right. And if that's not super clear, type or like write out U equals. At this point, we can do stuff with this. Like we could have tried to multiply out this thing right away. The problem with that is we'd still have an issue. There'd still be something like we don't know. Because like how do we do the antiderivative of X times square root of 2 minus X? We still would have had to do some trickery to get there. But this, we can work with this because the radical is rather simple. So let's simplify this, clean that up a little bit. All right, I'm going to stop. I want you to look at that for about 10 seconds and think of what questions do you have? Yeah. Yep, I just want to give people a chance to take a look and think about that. Like how both got to here. Absolutely. So I can show you a bit of that. Annotation. So to get here, the first thing I did is I distributed square root of U to each of these two terms. So I've got 3, or I've distributed negative square root of U to both of these. So I get negative 3 square root of u plus u times the square root of u. So that's distributing a negative square root to each of 3 and negative u. That's how I got here. Now there's the question of how do you get from this step to this one? All right. Well, to do that, remember that square root of u is also known as u to the 1/2. Okay. And that u is u to the first. Ooh, bright green. Let's do bright green. Bright green will be fun. So what that allows me to do is that this doesn't really change a whole lot and just comes right down to this, right? Because u to square root of u is also known as u to the 1/2. The question is, how does this piece become that? Well, if you have u to the first times u to the 1/2, that's equal to u to the 1 plus 1/2 power. It's a lot easier when I write on the iPad instead of writing with the mouse. So 1 plus 1/2 gives us 3/2 power. Is that what you were looking for about how to get them both there? Sweet. Fabulous. That was a good question. What other questions would you like to ask before we move on to the next piece? Okay. So on that note, I'm going to erase what's there just so I can move along and not have it. And this is being recorded, so you can always come back and check that out and the curation that goes along with it. Clear all drawings. And close annotation. All right, so the next piece here is we need to do the anti-differentiation. Now, to get there, the thing to notice, this is simpler to work with than what we had because both of these follow one of our basic integration rules. They follow our power rule for integration. For differentiation, what we do is we take the exponent, multiply the coefficient by that number, then subtract 1. For integration, especially since they're inverse operations, we do the exact inverse of that. So we add 1 to the exponent and then multiply by the reciprocal of the exponent, which is also known as dividing by what the new exponent is. So for this first one, I'm going to add 1 to 1/2, which we just talked about. 1 plus 1/2 is 3/2. And then I need to multiply -3 by 2/3, which is how I get -2 u to the 3/2. Well, u to the 3/2, I need to add 1 to that, which gives me 5/2, and then multiply by the reciprocal of that, which gives me 2/5. All righty. So at this point, now we're going to evaluate it, this expression at 0 and 3 and see what we get. So plug in 0, plug in 3, find the difference. The big thing to note about this, the nice thing whenever 0 is in there when you're calculating something, is that piece just basically disappears. And looking at this, it's minus all of that. So I distributed the negative to make this first part positive, the second one negative. Okay. So letting that disappear, you can see how that works out. And at 4 decimal places, I get the area, the area is 4.1569 approximately. Again, if at least 3 decimal places, whenever you use decimals, you need to do that. Otherwise, even if you have something correct to 2 decimal places, it's wrong. Okay, you need the 3 decimal places. So we went all through that. I want to show you that it was not for vain. Here's the original function. Here's the one after we did all the changing. What I wanted to show you was that they still give me the exact same answer, even though they look kind of different, or rather radically different. That's okay. You can publicly boo me about that or just privately boo me, whatever you need to do. So, but the big thing I want to point out here is that regardless of what the variable is, as long as you're careful about the way the substitution works, you get equivalent answers. You can see my calculator took a little longer to evaluate the U one, but both of these give you the same answer. And I'm showing you how to do it on a graphing calculator. But again, you could just go type this into Desmos as well, because again, I don't know what our availability of stuff is going to be. And I'm very skeptical about the fact that we're not going to have any times where we bounce back to complete virtual for this spring semester. But we'll see. Hoping for the best, though, because I just need to. All righty. That was the big thing that I really wanted to show you. Here's the unanimated version, so you can compare them against each other without just waiting for it, because you're like, crap, I missed it. I'll wait for it next time. And then crap, I missed it. Wait for it next time. That's all the big things I really wanted you to do. The graphing calculator, again, watch the keystrokes for this one. If you're using a graphing calculator that doesn't have the fancy math type, go check out what's it called on AP class, or on Desmos, not Desmos, one of the friggin' things. I'll show you. If you go to AP review packets and other resources, the 4 things on the AP calculator thing, that's the one you want. I'm going to make one for Desmos. It's on my docket, but everything keeps getting pushed back. What this will show you how to do is the keystrokes about how to do the 4 things you need to know how to do on the AP test. Again, graph function arbitrary window, numerically find a value, a 0 or an intersection, find a numerical derivative, and a numerical integral. And those are on this page. And they show you the setup. This is one of the first things I made like this. I probably can make it way better and more cool now. But that's how you set it up. With the new math type is so it looks the way you think it should, and you see it in books and stuff. That's math type. Again, I'll show you how to do those things and the order everything needs to go. Okay. So on that note, here is the assignment that goes along with this. Again, I wanted you to do those other 6 first, or try them, so that you had a little bit of background, so you could jump into these with some other, not completely hitting the ground running, maybe hitting the ground at a quick walk. So here's the assignment. I say due soon. And most of the time I just say that because, again, I don't want to give you a hard deadline, because I don't feel like this is the time for hard deadlines, except for the fact that the semester ends in next week, Friday. So I do need to have a hard deadline in this. So the hard deadline is the end of the semester. Keep working on your other assignments. I'm going to start putting in, start looking at the 4.6 assignments and any 4.4s that I have, and I'll go back and check all that stuff. So